I want to work out a specific example, and the example that I have chosen is the human centrifuge that is used by NASA in Houston for experiments on humans to see how they deal with strong accelerations. This is that centrifuge. The radius from the axis of rotation, the axis of rotation is here, and the distance from here to here, though you may not think so, is about 15 meters. So the astronauts go in here, and then the thing goes around. And so I would like to work out this with some numbers. The radius r, I'll give you light back, because it may be nicer for you. The radius is 15 meters. Depends, of course, a little bit on where the person is located in that sphere. It goes around 24 revolutions per minute. And that translates into 0.4 hertz. So the period to go around for one rotation is 2.5 seconds. The thing goes around once in 2.5 seconds. So the angular velocity, omega, which is 2 pi divided by t, if you take 2 pi and divide it by 2.5, it just comes out to be roughly 2.5, which is purely accident. That's the way it is. Don't ever think that that has to be the same, of course. It just happens to come out that way for these dimensions. So omega is about 2.5 radians per second. And the speed, the linear speed, tangential speed, if you want to call it, is omega r. That comes out to be about 37.7 meters per second. And that translates into about 85 miles per hour. So it's a sizable speed. What, of course, the goal is for NASA, what is the centripetal acceleration? That is omega squared. Or if you prefer to take v squared divided by r, you'll find, of course, exactly the same answer if you haven't made a slip, and that is 95 meters per second squared. And that is about 10 times the gravitational acceleration on Earth, which is really phenomenal. If you add to the fact that the direction is changing all the time when you go around, so you feel the 10g in this direction, and then you feel it in a different direction. I can't imagine how people can actually survive that. I mean, not faint. Most people like you and me, if we were to be accelerated along a straight line, not even a circle where the direction changes, but along a straight line, most of us faint when we get close to 6g. And there is a reason for that. You get problems with your blood circulation, and not enough oxygen goes to your brains, and that's why you faint. How these astronauts can do it at 10g and the direction changing all the time, it beats me. If you take a Boeing 747, it takes 30 seconds from the moment that it starts on the runway until it takes off. You should time that when you get a chance. It's very close to 30 seconds. And by that time, the plane has reached a speed of about 150 miles per hour. And if you assume that the acceleration is constant, it's an easy calculation, it turns out that the acceleration is only 2 meters per second squared. That is only 1/5 of the gravitational acceleration. It feels sort of good, right? It's very comfortable when you're sort of taking off, and it's only 2 meters per second squared. These poor people, men and women, 95 meters per second squared.